Welcome to a journey into the next frontier of technology. Today, we explore how the Internet as we know it is about to undergo its most profound transformation since its creation. The quantum Internet isn't just an upgrade, it's a complete reimagining of how information travels across our planet, using the strange and powerful properties of quantum mechanics. From China's groundbreaking 4,600-kilometer network to the global race for quantum supremacy, we'll uncover how entangled particles are creating unhackable communication channels and why this technology represents not just a scientific breakthrough, but a geopolitical chess piece in the 21st century's technological competition. Our digital world has transformed human civilization in ways unimaginable just decades ago. Classical computing and networking have connected billions of people, revolutionized commerce, and put the sum of human knowledge at our fingertips. But these systems operate within the constraints of classical physics, the same laws that govern everyday objects. These limitations aren't just technical hurdles, they represent fundamental boundaries on what's possible with traditional information processing. The quantum Internet represents something far more revolutionary than faster download speeds or more reliable connections. It harnesses the counterintuitive properties of quantum mechanics, the physics that governs the behavior of particles at the smallest scales, to create communication channels with capabilities that would be impossible under classical physics. This isn't merely improving existing systems, it's opening doors to entirely new possibilities in how information can be transmitted, secured, and processed across the globe. In October 2023, China quietly achieved what many experts consider the most significant milestone in networking since the creation of the Internet itself. Chinese quantum scientists successfully established the world's first integrated quantum network spanning over 4,600 kilometers, a distance that would stretch from New York to Los Angeles. What makes this achievement remarkable isn't just the scale, but the implementation. This network combines both fiber optic ground connections and satellite-based quantum key distribution, creating a hybrid system that overcomes many of the distance limitations that have challenged quantum communications. Unlike theoretical demonstrations or laboratory experiments, this represents the most advanced practical implementation of quantum Internet technology to date. The network doesn't just exist, it works, demonstrating functional quantum key distribution across distances that would have seemed impossible just a few years ago. While Western media gave this breakthrough surprisingly little attention, its significance cannot be overstated. China has established a functional quantum communication infrastructure that is fundamentally different from the classical Internet we use daily. China's early lead in quantum networking has accelerated what was already becoming an intense technological competition. The European Union has committed over €1 billion to its Quantum Communication Infrastructure Initiative, with the ambitious goal of developing a quantum network spanning the entire continent by 2027. This isn't just a research project, it's a strategic infrastructure investment with both economic and security implications. The United States is pursuing a parallel path through the Department of Energy, which has established a national quantum Internet backbone connecting its major research laboratories. This network, still in its early stages, has plans to expand to university and commercial partners, creating a quantum communication ecosystem that could eventually rival or surpass China's current capabilities. Japan, too, has made significant investments in quantum communication technology, focusing particularly on satellite-based systems that could eventually form part of a global quantum network. What makes this technological race particularly fascinating is that it differs from previous competitions in computing or telecommunications. Quantum networks require expertise across multiple disciplines, from fundamental physics to materials science to information theory, creating unique challenges in workforce development and research coordination. Nations aren't merely competing on research funding but on their ability to translate theoretical breakthroughs into engineering realities and build the specialized workforce needed to maintain and expand these systems. At the heart of quantum networking lies a phenomenon so counterintuitive that even Einstein struggled to accept it, famously calling it spooky action at a distance. Quantum entanglement occurs when particles become linked in such a way that the quantum state of each particle cannot be described independently of the others. This connection persists regardless of how far apart these particles travel. When one entangled particle is measured, its corresponding partner instantaneously reflects complementary properties, seemingly defying the speed of light limitations that govern all other interactions in the universe. This isn't theoretical physics, it's the practical foundation of quantum networks. In implementation, quantum networks distribute these entangled particles between nodes, creating correlations that can be used to generate encryption keys or transmit information in ways impossible with classical bits. The most widely implemented application is quantum key distribution, or QKD, which uses these entangled states to generate encryption keys that are theoretically impossible to intercept without detection. This security stems from a fundamental principle of quantum mechanics: the act of measuring a quantum state disturbs it. Any attempt to eavesdrop on quantum communications immediately reveals itself by altering the expected correlations between entangled particles. This creates a communication channel that isn't just difficult to hack, it's physically impossible to compromise without detection, representing a fundamental advance in secure communications. Building a quantum internet requires entirely new physical infrastructure that differs significantly from classical networks. At each network node sits a quantum processor capable of manipulating quantum states, creating, storing, or measuring them as needed. These nodes are connected by quantum channels, which can be either fiber optic cables similar to those used in classical networks, or free space channels that allow quantum information to travel through the air or vacuum of space. The most critical components are the interfaces between quantum and classical systems, where information must transition between these fundamentally different domains. Photons, particles of light, typically serve as the quantum information carriers of choice. They're ideal because they interact minimally with their environment, reducing decoherence, and they travel at the speed of light, minimizing transmission time. Current implementations primarily use what are called prepare and measure protocols. In these systems, quantum states are created at one location, transmitted through quantum channels, measured at their destination, and then used to derive secure encryption keys. This approach works for quantum key distribution but has distance limitations. The next generation of quantum networks aims to implement true quantum repeaters, devices that can extend entanglement without measuring the quantum states, preserving their quantum properties across global distances. These would enable more advanced applications beyond secure key exchange, including distributed quantum computing and quantum teleportation of information states. Despite recent breakthroughs, quantum internet development faces significant technical challenges that must be overcome before global implementation becomes reality. Perhaps the most fundamental is quantum memory, the ability to store quantum states for practical periods without losing their quantum properties. Recent research published in Nature Communications has demonstrated quantum memory with coherence times approaching several minutes using rare earth-doped crystals cooled to near absolute zero. While this represents an order of magnitude improvement over previous capabilities, it remains insufficient for practical global networks that would require storage times of hours or days. Quantum repeaters, which would extend the range of quantum communications by managing entanglement across longer distances, remain in early experimental stages. Without effective repeater technology, quantum networks require either direct connections between points, limiting their range, or trusted nodes that potentially introduce security vulnerabilities by measuring quantum states during transmission. The fundamental challenge stems from quantum decoherence, the tendency of quantum systems to lose their quantum properties when interacting with their environment. Creating effective quantum memory requires isolating quantum systems from environmental noise while simultaneously allowing controlled interactions for information processing. Researchers are exploring various physical platforms to solve this challenge, including trapped ions, nitrogen vacancy centers in diamond, and superconducting circuits. Each approach offers unique advantages and limitations for quantum memory implementation. The quest to develop practical quantum memory represents not just an engineering challenge but a fundamental scientific frontier. Success would enable not only quantum networking but more powerful quantum computing architectures and potentially new insights into quantum mechanics itself. While unhackable communications represent the most immediate and practical application of quantum networks, the potential extends far beyond enhanced cybersecurity. One of the most promising applications is distributed quantum computing, which would allow multiple quantum computers to work together on problems beyond the capacity of any single machine. This networked approach could accelerate the timeline for practical quantum advantage in fields ranging from drug discovery to materials science. Quantum sensing networks represent another revolutionary application. By networking quantum sensors that can detect minute gravitational, magnetic, or electromagnetic anomalies, scientists could develop unprecedented capabilities in fields ranging from geology to medicine. Imagine early warning systems for earthquakes that detect subtle gravitational changes days before conventional sensors, or new medical imaging techniques that can visualize biological processes at the cellular level without invasive procedures. Perhaps most intriguingly, the quantum internet might enable entirely new forms of scientific collaboration. Astronomers could link quantum-enhanced telescopes to create virtual instruments with effective apertures spanning continents, achieving resolution impossible with any single telescope. Physicists could conduct experiments testing the foundations of quantum mechanics across global distances, potentially resolving long-standing questions about the nature of reality at the quantum level. As these networks evolve from regional experiments to global infrastructure over the next decade, they may fundamentally transform not just our technological capabilities but our understanding of computing and physics itself. They could create an internet that operates on principles that challenge our classical intuition while opening doors to technologies currently confined to theoretical speculation or science fiction. The race for quantum communication supremacy carries implications that extend far beyond technological achievement. The nation that establishes the first truly functional global quantum network gains advantages across multiple domains: military, intelligence, economic, and diplomatic. Quantum communications would provide military and intelligence agencies with communication channels that cannot be compromised by adversaries, representing a significant strategic advantage in both peacetime intelligence gathering and potential conflicts. The economic leverage gained by controlling quantum communication infrastructure in an increasingly data-driven global economy cannot be overstated. Just as control of shipping lanes, railroads, or oil pipelines has conferred economic power throughout history, quantum communication pathways may become the critical infrastructure of the 21st century information economy. Nations that develop this technology first will set standards, control access, and potentially extract premiums for its use. This technological competition is already reshaping international relations and research collaboration patterns. Countries are increasingly treating quantum technology as a national security priority, restricting information sharing and implementing export controls on key components. Simultaneously, new international partnerships are forming between nations pooling resources to compete in this high-stakes technological race. The quantum internet represents not just a technological revolution but a geopolitical inflection point that may reshape power dynamics in the coming decades. The evolution from today's experimental quantum networks to a truly global quantum internet will likely follow a path similar to the classical internet's development, but with unique challenges and accelerated timelines. The first phase, which we're currently experiencing, involves regional quantum networks connecting research institutions and government facilities. These networks primarily demonstrate the technology's feasibility and provide secure communications for high-priority applications. The second phase will likely see the integration of commercial and academic users into these networks, with quantum key distribution becoming available to financial institutions, healthcare providers, and other organizations handling sensitive data. As quantum repeater technology matures, these regional networks will begin connecting across continents, first through trusted nodes and eventually through true quantum repeaters maintaining end-to-end quantum states. The final phase would be a fully quantum-enabled global network where quantum and classical communications work in tandem, with classical channels handling everyday data and quantum channels providing security and enabling new applications. This transition will require not just technological development but new international agreements on standards, protocols, and access rights. Unlike the relatively organic development of the classical Internet, the quantum Internet's global implementation will likely require more coordinated international effort due to its complexity and strategic importance. Despite the challenges, the potential benefits of a global quantum Internet, from unprecedented security to revolutionary scientific capabilities, provide powerful incentives for continued investment and development. The question isn't whether a global quantum internet will emerge, but when, and under whose influence it will develop. Recent advances in quantum memory represent some of the most significant breakthroughs in quantum networking technology. The ability to store quantum states reliably is the linchpin for advanced quantum networks, and researchers are pursuing multiple promising approaches. The rare earth-doped crystals mentioned in Nature Communications represent just one avenue. These specialized materials, when cooled to temperatures approaching absolute zero, can maintain quantum coherence for minutes rather than the microseconds or milliseconds previously possible. Other approaches include using the nuclear spins of atoms trapped in diamond lattice defects, known as nitrogen vacancy centers. These systems have demonstrated remarkable stability even at room temperature, potentially reducing the need for extreme cooling in some applications. Superconducting circuits offer another promising platform, leveraging the quantum properties of Josephson junctions to create quantum memory elements that integrate well with quantum computing hardware. Each approach has distinct advantages. Rare earth crystals offer longer coherence times, diamond defects work at higher temperatures, and superconducting circuits provide easier integration with existing quantum processors. The breakthrough that ultimately enables practical quantum memory may come from combining these approaches or from entirely new materials yet to be discovered. What's clear is that quantum memory research has accelerated dramatically in recent years, with coherence times improving by orders of magnitude. As this technology matures, it will remove one of the primary bottlenecks in quantum network development, potentially accelerating the timeline for practical quantum internet implementation from decades to years. Quantum repeaters represent perhaps the most challenging component needed for a truly global quantum internet. Unlike classical repeaters that simply amplify signals, quantum repeaters must extend entanglement without destroying the quantum information, a fundamentally different and more difficult task. The theoretical framework for quantum repeaters involves a process called entanglement swapping, where entanglement between adjacent network segments is extended across longer distances without direct interaction between the endpoints. Early experimental implementations have demonstrated this principle, but practical devices capable of operating reliably in real-world conditions remain elusive. The most promising approaches combine quantum memory with precise quantum gate operations to perform entanglement swapping. When two particles from separate entangled pairs interact through a quantum gate operation, their partners can become entangled despite never having interacted directly. By chaining these operations together across multiple network nodes, entanglement can theoretically be extended across arbitrary distances. Recent experiments have demonstrated entanglement swapping across distances of hundreds of kilometers, but with success rates and fidelity that remain too low for practical applications. The breakthrough will likely come from integrated devices that combine efficient quantum memory, precise quantum gates, and error correction mechanisms in a single system optimized for network operation rather than general-purpose quantum computing. As with many aspects of quantum technology, progress in quantum repeaters follows an exponential rather than linear trajectory. What seems impossibly distant today may become practical reality within a decade as researchers build on each incremental advance. The boundary between quantum and classical information represents one of the most fascinating and challenging aspects of quantum networking. Quantum information, with its ability to exist in superpositions and entangled states, offers powerful new capabilities but must ultimately interface with classical systems that users can interact with. This quantum classical interface requires specialized hardware and protocols that can translate between these fundamentally different information paradigms. At a physical level, this interface often involves devices that can convert between photonic quantum states used for transmission and electronic or atomic states used for processing and storage. These conversion processes must maintain quantum coherence while achieving high efficiency, a significant engineering challenge. At the protocol level, the interface must manage the flow of information between quantum and classical channels, determining which data requires quantum transmission for security or other quantum advantages, and which can remain in classical channels for efficiency. This creates a hybrid network architecture where quantum and classical communications work in tandem rather than replacing one another. Perhaps most importantly, the quantum classical interface must be accessible to users without specialized quantum physics knowledge. Just as today's Internet users don't need to understand TCP/IP protocols to send an email, tomorrow's quantum Internet users will need intuitive interfaces that abstract away the quantum complexity while delivering its benefits. Developing these user-friendly interfaces represents not just a technical challenge but a design and user experience challenge that will determine how quickly quantum networking technology can be adopted beyond specialized scientific applications. While secure communications receive the most attention, quantum sensing networks may ultimately deliver the most transformative applications of quantum networking technology. Quantum sensors leverage quantum properties like superposition and entanglement to achieve measurement precision beyond what's possible with classical sensors. When these quantum sensors are networked together, entirely new capabilities emerge. Gravitational sensing networks could revolutionize geology and natural disaster prediction. By detecting minute changes in gravitational fields with quantum sensors distributed across fault lines, scientists could potentially identify precursor signals days before earthquakes occur, saving countless lives. Similar networks could detect underground resources or monitor ice mass changes in polar regions with unprecedented precision. In medicine, networked quantum sensors could enable new imaging modalities that visualize biological processes at the molecular level without radiation or invasive procedures. Quantum sensors detecting subtle electromagnetic signals from neural activity could create brain imaging systems orders of magnitude more precise than today's technologies. For fundamental physics, quantum sensor networks could search for dark matter, detect gravitational waves from new sources, or test quantum mechanics at unprecedented scales. The power of these networks comes not just from the quantum advantage of individual sensors but from their ability to correlate measurements across distance and time, filtering out local noise and identifying patterns invisible to isolated sensors. As with many quantum technologies, the most revolutionary applications may be those we haven't yet imagined, new ways of sensing and measuring the world that become possible only when quantum effects are harnessed across networked systems. As quantum Internet technology transitions from theoretical possibility to engineering reality, research priorities are shifting. Early quantum networking research focused primarily on fundamental questions: can entanglement be distributed? Can quantum states be teleported? Can quantum key distribution work in real-world conditions? With these questions largely answered affirmatively, research is now addressing the engineering challenges of practical implementation. Material science has become central to quantum networking research, with scientists searching for better quantum memory materials, more efficient single-photon sources, and room-temperature quantum components that don't require extreme cooling. Engineering disciplines are tackling the integration challenges, developing systems that combine quantum and classical components in reliable, manufacturable packages. Computer science researchers are developing the protocols, algorithms, and software stacks that will make quantum networks usable beyond physics laboratories. This broadening of the research community reflects the technology's maturation. What began as specialized physics research now encompasses multiple disciplines working together toward practical implementation. Funding patterns reflect this shift, with government programs increasingly emphasizing applied research and commercialization pathways alongside fundamental science. As with the classical Internet's development, we're likely to see accelerating progress as theoretical advances, engineering improvements, and commercial applications create virtuous cycles of innovation. The quantum Internet may still seem like science fiction to many, but to researchers in this rapidly advancing field, it's becoming an engineering roadmap with increasingly well-defined milestones and timelines. Within a decade, quantum networking may transition from specialized research to critical infrastructure, following a trajectory similar to other transformative technologies throughout history. The quantum Internet represents far more than just the next generation of digital communication. It embodies a fundamental reimagining of how information travels across our world. By harnessing the counterintuitive properties of quantum mechanics, particularly entanglement, scientists and engineers are creating networks with capabilities that defy classical physics and open doors to applications we're only beginning to imagine. From China's groundbreaking 4,600-kilometer network to competing initiatives across Europe, America, and Japan, we're witnessing a global race with profound geopolitical implications. The technical challenges remain significant: quantum memory limitations, the need for practical quantum repeaters, and the complex quantum-classical interface all require further breakthroughs. Yet the accelerating pace of research suggests these hurdles will be overcome sooner than many expect. Beyond unhackable communications, the quantum Internet promises revolutionary applications in distributed quantum computing, networked quantum sensing, and scientific collaboration that could transform fields from medicine to astronomy. As this technology transitions from specialized laboratories to global infrastructure over the coming decade, it will likely reshape not just our technological capabilities but our understanding of information itself. The quantum Internet stands as one of humanity's most ambitious technological projects, a network that operates on principles Einstein once found too strange to accept, yet which may soon become the foundation of 21st-century communications, computation, and scientific discovery. Thanks for watching. Please like, subscribe, and hit the bell icon for updates. Your feedback is appreciated. We hope to see you again.